we have already discussed the basic or the fundamentals of the sampling theory, and why we need sampling theory, and how we are doing samples for like how we are converting the continuous signal to the discrete signal. We have already discussed all these information in our previous lecture. In this lecture we are going to discuss few cases, like if you are doing the sampling, then there are few cases that you need to consider. Case 1: if your sampling frequency should be much bigger than 2 of FM, then you can have the samples like this. So your sample will be like this. And so on. Similarly on the negative side. And so on. So it means that you can see the separation. So you can see the separation. So you can see you can easily construct by using the low pass filter. So the samples are not overlapping. There is much separation or much gap between these samples, and you can using the low pass filter, you can easily extract the message signal. Like you can use the low pass filter here. So this is the low pass filter. So if you use low pass filter, so you can easily extract the message signal. So that is your X of W. But the second case is that if your sampling frequency is equals to 2 times the modulating frequency, so it means that sample just touches each other, and this is also known as the Nyquist rate or the Nyquist criteria. So if Fs is equals to 2 Fm, so it means that your samples are like, because these curves, they expand in this way, so they just touch like this, so like this. Similarly on the negative side. So still by using the low pass filter, you can see, still by using the low pass filter you can still extract the message signal if this is the sampling frequency, and this is also known as the Nyquist rate. But the third case is when your sampling frequency is less than twice the FM, so this is undersampling, and you can call this case aliasing, like aliasing effect. So effect of undersampling, which is also known as aliasing effect. So if this is happening, so what happens then? So in this case, you can say that your signal, so your like samples start overlap. So like this one coming to this way, and similarly this side like entering into the other samples. Similarly this one is entering here, and this one will be entering there. So this one will be entering there. So similarly, so you see this one is entering there. So and then this one is entering here. So you can see. So this is overlap. This area is known as overlapping. This area is overlapping. So this is overlapping, or you can say a distortion. So if this is happening, so when you use low pass filter, in the low pass filter you are getting both signals, like you are getting high frequency component as well as the low frequency component. So that is why you are getting distortion in your message signal, like you are getting two different frequencies. So if you are getting two different frequencies, then it is very hard to extract the information. Due to aliasing effect, it is not possible to recover original signal xt by using the low pass filter, because your message is distorted. So before sampling, if we pass the original message, so if like you wanna overcome this effect, so this is the solution. Like either you can pass your original signal through the low pass filter before sampling. So this is also known, the filter is also known as a pre-aliased filter. So by passing through low pass filter, we are limiting the signal to FM. Like because we know that the signal is a combination of higher frequencies and low frequencies, but when we pass that signal through the low pass filter whose cutoff frequency is FM, so whose cutoff frequency is FM, so then we are getting the signal only FM, then it is easy to get the sampling frequency twice the modulating frequency. Like in this case you are limiting the signal, so that is why you are limiting the signal only to FM, so that is why this filter is also known as band limiting filter. So to conclude that how you can avoid oversampling, or how can you avoid the aliasing effect. So there are two solutions. The first, you can use pre-aliased filter. The second solution is that you must always satisfy this condition that the sampling frequency is bigger than the modulating frequency. So let's do some numerical, and then we can understand a bit more. So this is the signal 10 cos 60 pi t plus 5 cos 400 pi t minus sin 200 pi t, and you need to calculate the Nyquist rate for this signal. We know that the Nyquist rate is f of s is equal to 2 twice the fm. Like this is the Nyquist rate, f of s is equal to 2 of fm, but we need to know what is fm. So fm is the maximum frequency. But what is maximum frequency? So there are three frequency components, like you can see. So we can say that your f1 is, because this is in term of omega, so omega 1 by 2 pi. So what is this? Is omega 1. So this is omega 2. So this is omega 3. So omega 1 is 60 pi by 2 pi, so which is equals to 30 hertz. Similarly, so your f2 is omega 2 by 2 pi, which is equals to 400 pi divided by 2 pi, so that is equals to 200 hertz. So and f3 is equals to omega 3 by 2 pi, which is equals to, what is omega 3? 200 pi divided by 2 pi, so that is equals to 100 hertz. So fm is basically the maximum of all. So maximum of all, so this is 30, this is 200, this is 100. fm is 200 hertz. So your Nyquist criteria is 2 times fm, so which is equals to 2 multiplied by 200, so that is equals to 400 hertz. So we have second question. Example, find the Nyquist rate and Nyquist interval for the signal x of t is equals to 1 over 4 pi cos 6000 pi t and cos 2000 pi t. So this is product. So we have to convert them into the addition or subtraction thing. So in order to see which are the frequency components over there. So let's first convert that into the product. So we know that this is 2 cos a cos b is equals to cos a plus b plus cos a minus b. So we can write same thing. So we multiply and divide by 2. So that is equals to 8 pi into 2 cos 6000 pi t cos 2000 pi t. So using that formula we can write 1 over 8 pi. So that is equals to cos 6000 pi plus 2000 pi t plus cos 6000 pi minus 2000 pi t. So that is equals to 1 over 8 pi. So cos 6 and 2 8000 pi t plus cos 6 2, so that is 4000 pi t. So these are the two frequency component. This is omega 1, this is omega 2. So f1 is equal to omega 1 by 2 pi. So omega 1 is 8000 pi by 2 pi. So that is equals to 4000 hertz. f2 is equals to omega 2 by 2 pi. So omega 2 is 4000 pi divided by 2 pi. So that is equals to 2000 hertz, or you can say it's a 4 kilohertz or 2 kilohertz. So what is FM? So FM is the maximum of these two. So maximum of these two is 4000 is maximum, so that is equals to 4000 hertz. So the first one was Nyquist in rate. Nyquist rate Fs is equal to 2 of Fm, so 2 multiplied by Fm was 4000, so that is equals to 8000 hertz. Second is the Nyquist interval. Means the duration Ts, so Ts is equals to 1 over Fs, or you can say 1 over 2 Fm, both are correct. So Ts is equals to 1 divided by 8000. So if you divide 1 by 8000, so you can write, so this is the seconds, 1 by 8000 seconds. So I hope you understand the procedure of the sampling theory and all the cases of the sampling theory that we have, like undersampling, Nyquist criteria, and the clean version of the sampling. And we have solved few examples as well, and we have calculated the Nyquist rate and the Nyquist interval for better understanding. But still, if you have any question, you are most welcome. You can write the question in the comment box. We will answer the questions. Thank you for watching the video.